This is Jack Jackson. We're going to continue our look into the Fundamental Theorem of Calculus. In this video, we're going to kind of reverse the order from our last video. So if you remember in the last video, we looked at a function of x, or of t here, and we integrated from some a up to x, that function of t, and then took the derivative with respect to x. That gave us back our original function f evaluated at x. So if we integrate first, then take a derivative, we get the function that we end up with, that we started with. We end up with what we started. Well, what if we, so this is integration first, then derivative. What if we sort of start the other way around? What if we take a derivative of some function and then integrate it? So here we're starting with some function f of t, and then we're actually taking the derivative, f prime, and then we want to integrate that, let's say, from 0 to x, or from some a to x. So let's start by using the function f of t equals t to the fourth. Now, as in our last video, I want you to take your graphing calculator out and work with me through these through this investigation. And in fact, there'll be time to time that I'll ask you to stop and maybe work through something on your own and then check it with what we're doing next on the video. So put that into y1. Of course, you'll have to write it in as a function of x, so it'll be x to the fourth. At this point, turn off y1 and clear out the rest of the functions, but do that. Now compute the derivative of this, f prime of x, using the usual differentiation shortcut rules. Put it into y2, and then let's use the numerical derivative of y1, put that in y3, and check to make that y2 and y3, check to make sure those tables are the same to check your derivative formula. Good practice doing that. So if you would, go ahead and get your calculator out, try out that. When you've satisfied that you've got all that worked out, then come back to the video. Press pause now. Okay, well, you're back. Hopefully now you've done something like this. Here's a TI-80 for newer operating system, what it looks like. So you put in the formula that we're using, x to the fourth for y1, take the derivative, which is 4x cubed, then take the numerical derivative, which is really a symmetric difference quotient, an approximate derivative of this by doing math 9, numerical derivative of y1 with respect to x, evaluated at x equal x. Okay, and then we check the tables and we see that for sure, sure enough, y2 and y3 do match up. Now, what we want to do now is integrate that derivative. So we're going to integrate, well, we can either integrate y2 or y3, and it should be basically equivalent there. Of course, y2 is the exact formula for the derivative. y3 is the numerical derivative. But so either way, suppose we do y2, the integral, and look at the table now of y1 and y4. And you see that they turn out to be the same. Notice we should have gotten the same thing if we do the derivative, do the integral of y1. y2 or y3. So here, what are we doing? We're doing the derivative first. And so we found the derivative of t to the fourth, and then the integral from 0 to x of that was x to the fourth. Now, let's keep going with this a minute. We're not done yet. So change the formula. What if we change the formula to x to the fourth, say, plus 3? The derivative is still 4x cubed, and that still checks out. But if we do then I do y4, which was, remember, the integral of y3. The y3 is the numerical derivative, so I did it that way. So now I'm not really using y2. I could get rid of it if I wanted to. And notice that y1 and y4, wait a minute, they're not quite the same this time, are they? Well, how far off are we? Let's look. Well, notice at 0, y4 says we should get 0. y1 is actually 3. So that's off by 3. And this is 4 to 1, 19 to 16. Can you see a relationship there? Hopefully you see that the y4 is just 3 smaller than the y1, and the 3 was this y value when x is 0. Does that make sense? Hopefully that does. Let's keep going a little bit. So it looks like maybe what we could do is, if we put in our function whatever it is in y1, we take the derivative of it, say with y3, numerical derivative, turn around and take that y3, integrate from 0 to x, but add on to that y1 of x. Now see what, y1 of 0, excuse me. Here's the rest of it, looks like this, y1 of 0. And see what happens? Now the tables do match up. So let's try it for another lower bound. Instead of 0, let's change it to something else. So here's what I did. I just took my calculator and took some number, just a random number, like I said 5, and store it as a from the home screen. And then when I did this setup, I replaced the 0 by whatever a happens to be at the moment, which is at the moment it's 5. Substitute that in for a, but then I did this as y1 of a. Now check that out. See if that works out. Do that on your own calculator and see if you can get this screen here, or these set of screens here. And if you look, we got the same y1 as we did y4. Now if I put in a different value for a, like say -2, look what happens. Again, I get the same values for y1 and y4. So it didn't matter really where we started, as long as we added on that y1 of a. That's how much we would be off. Now, here's the next thing. Try putting in a different formula for y1. Just pick anything you want. So pick whatever formula you want for y1. See if this works. Now in this case, just delete y2 because we're actually using the numerical derivative of y1 and then doing the numerical integral of that plus y1 of the a. So we're doing the numerical derivative of y3 from a to x and then taking that and adding on y1 of a. And the question is that back to my original function? Does y1 and y4, do they look the same in the table? And the answer should be yes. Okay, if you need to, pause, check that out for a couple examples and make sure that that does make sense to you and that does check out. When you're satisfied you have that, come back. Press pause now. Well, here I did it with another one myself. I did e to the power x plus 5x. I could find the derivative and use it for instead of y3. Actually, it's not hard to do. It's just e to the x plus 5. But you know, regardless, I can use the numerical derivative here and not even have to worry about the formulas. So I have e to the x plus 5x. Take the derivative of that with respect to y, of the y1 with respect to x, and evaluate it at arbitrary x. So derivative first. Take that derivative of y1 and integrate it from a to x, definite integral, and add on to that y1 of a, and you see that the table for y1 and y4 are the same. We're right back where we started. So evidently, what do we get to work out? We got to work out this basic result, that if you take a derivative of a function and you integrate it between two values, say a and x, you get f of x minus f of a. That's kind of interesting. So it's equivalent to saying the following: if you integrate from a to b, f prime of t dt, you get f of b minus f of a. So a definite integral can be found by finding a function whose derivative is what you started with. So notice we're starting with the derivative of this function f. We don't know the function f, we know the derivative. So what we need to do is to reverse that process. We need to find a function whose derivative is the function that we are given, that is the integrand, the thing we're integrating. Well, this process is the opposite of the process of finding a derivative. It's the inverse process. And so what we're doing here is trying to find an antiderivative. So what this says is we can evaluate this definite integral if we can get our hands on an antiderivative, then we just evaluate it at the two endpoints. So we have discovered now what Newton and Leibniz discovered, and what was in 1667 the crowning achievement of 4,000 years of mathematics, and certainly one of the crowning jewels of mathematics to this day, the Fundamental Theorem of Calculus. And so the Fundamental Theorem of Calculus says let f of t be a function that's continuous on the interval, closed interval from a to x. Okay, then we have two results. Number one, if we integrate f of t dt from a to x, and then take the derivative with respect to x, we'll be back at the original function f evaluated at x. And part two, if we integrate from a to x the derivative of f of t dt, we get a net change in the antiderivative. We get f of x minus f of a. So we're going to come back in our next video and investigate this fundamental theorem a little bit more and give a proof, or at least maybe a little bit informal in a couple of cases, but basically a proof of this fundamental theorem of calculus to get an even better idea of what it means.